Good evening, everyone. Hope you're all doing well, safe, and secure. It gives me a great pleasure in welcoming all for this international webinar. The Department of Mechanical Engineering of
Good evening,
Vidyavardhaka College of
everyone.
Engineering,
Hope
in
you're all
association
doing
with
well, safe,
ISRE
and
Mysore chapter,
it
is
gives me a
organizing
great
this
pleasure
international
in
webinar.
welcoming all
We
for
are
this
really grateful
international
to
webinar.
many people in helping us to organize this international webinar. Dear friends, today we have a big man, a celebrity in the field of energy research, Dr. S A Sherif, professor in the Department of Mechanical and Aerospace Engineering, Gainesville, University of Florida, United States of America. He will be privileged to deliver a talk on latest advances in energy research and drive to net zero energy. Dear participants, net zero energy concept is one of the hot favorites for the researchers, academicians, exclusively to explore in research. To begin the program, it is very much official to do the welcome address. Initially, it gives me a great pleasure in welcoming the resource person, Dr. S A Sherif, to this webinar. Welcome to you, sir.
Thank you.
Additionally, I wish to welcome the torch bearer of this institution, the principal of Vidyavardhaka College of Engineering, Dr. B. Sadashive Gowda, for his gracious presence. Welcome to you, sir. It gives me immense pleasure in welcoming the driving force of Department of Mechanical Engineering, the head of the department, Dr. G.V. Naveen Prakash, for this international webinar. Welcome to you, sir. It gives me immense pleasure in welcoming the President, ISRE Mysore Chapter, Srimati H.M. Sujata, to this webinar. Welcome to you, Madam. It gives me immense pleasure in welcoming the President-elect of ISRE Mysore Chapter, Sri D.K. Dinesh Kumar, Treasurer of ISRE Mysore Chapter, Sri Anil Kumar Nadige, Program Coordinator of ISRE Mysore Chapter, Sri P.V. Bharadwaj, for this international webinar. Additionally, it gives me immense pleasure in welcoming the organizing committee members in taking a strong initiative to organize this international webinar. Friends, before we move further, I request my colleague, Dr. Khalid Imran, to introduce the signature of this webinar, Dr. S A Sherif. Over to Dr. Khalid Imran.
A very good afternoon to all. This is Dr. Khalid Imran, organizing member of this international webinar. It is a great honor and privilege to introduce today's speaker, Dr. S A Sherif, to all beloved participants. Dr. S A Sherif is a tenured professor of mechanical and aerospace engineering and founding director of Wayne K. and Laila L. Masoor HVAC Laboratory, the director of Industrial Assessment Center, and the director of the Mobile Energy Laboratory at University of Florida. He served as the co-director of the Southeastern Center for Industrial Energy Intensity Reduction at the University of Florida from 2009 to 2013. He is a life fellow of ASME, that is American Society of Mechanical Engineers, a life fellow of ASHRAE, that is American Society of Heating, Refrigerating and Air Conditioning Engineers, a fellow of Royal Aeronautical Society, an associate fellow of AIAA, that is American Institute of Aeronautics and Astronautics, vice president of Commission B2 of the International Institute of Refrigeration, a member of Advisory Board of Directors of the International Association for Hydrogen Energy, and a founding member of the Board of Directors of the American Society of Thermal and Fluid Engineers, that is ASTFE. He currently serves as a program evaluator for ABET, that is Accreditation Board for Engineering and Technology in Mechanical Engineering, from 2019 to 2024. He also currently serves as technical editor of ASME Journal of Solar Energy Engineering and the immediate past technical editor of ASME, that is Journal of Thermal Science and Engineering Applications. He currently serves as subject editor, associate editor, and a member of editorial advisory board of 22 other thermal science journals, such as Applied Thermal Engineering, Heat Transfer, Asian Research, the International Journal of Energy, and Solar Energy. Dr. Sherif has given over 150 invited lectures worldwide and received numerous awards from ASME, ASHRAE, AIAA, ASTFE, and the Japan Society of Mechanical Engineers and NASA. Dr. Sherif has over 400 publications, 22 book chapters, 1 book, and 2 US patents. I once again welcome you, sir. Thank you very much.
Thank you very much for the kind words.
Thank you, Dr. Khalid Imran, for your very persuasive, elegant, and eloquent introduction of the international celebrity, Dr. S A Sherif.
Thank you very much, sir.
Then to Dr. S A Sherif, he will be delivering a talk on latest advances in energy research and drive to net zero energy. I request Dr. S A Sherif to start the session.
Thank you very much. It's a pleasure to be with all of you. And I'd like to say good morning for those who are watching from the United States, and good afternoon to those in India, and evening to those in China, perhaps. I would like to talk to you today about the latest advances in energy research and the drive to net zero energy. The presentation is going to be covering several topics. One of them is the difference between energy carriers and energy sources. And then I'll give you some background on the energy usage in the United States, and talk to you a little bit about the goals established by the Department of Energy here in the country, the United States. Strategy employed, and it's divided into the energy efficiency component and the use of renewable energy component. Then I'm going to talk to you in some detail on the road to getting to zero. I'll talk to you about the status report from the New Buildings Institute, as well as other organizations that are working towards achieving net zero. I'll tell you a little bit about the statistics of the first 10 zero energy buildings in the United States, and give you an example of the one in Kukuni Village in Hawaii. We'll talk to you about the California experience and give you some examples of recent energy efficiency projects that have been funded by the U.S. Department of Energy, and then talk to you about some concluding remarks. First, let us define the difference between energy carriers and energy sources. Energy carriers are not energy sources. They carry energy, but they are not able to produce energy on their own. Examples are gasoline, hydrogen, and electricity. All of those are energy carriers. They're not energy sources. Energy sources are able to have they're called primary energy sources, such as solar energy, nuclear energy, coal, oil. And the idea is to use these energy sources to produce energy carriers. Without energy sources, you cannot produce energy carriers. even though hydrogen, for example, as an energy carrier is abundant in nature, the most abundant element in nature, it actually does not exist in atomic form, and as a consequence, it needs to be produced. So you have it, for example, in water and H2O, but you have to be able to produce hydrogen from water, perhaps using electrolysis, and perhaps with the use of the primary energy source such as solar energy. This is a slide showing the U.S. projected energy consumption. The Energy Information Administration published these data from time to time. You can see the energy consumption broken down in terms of the primary energy sources, both from the renewable side as well as from the non-renewable side. Of course, oil and other liquids constitute about 37%, coal 21%, nuclear 9%, natural gas 25%, liquid biofuels 1%. And all of those, in fact, all of those five are more or less either fossil fuel based or nuclear. And therefore, the renewables are very small. The percentage of renewables continues to be small. It went from 7% in 2010 to 11% in 2035, which is what we're hoping to achieve. But you can see that that is not ambitious enough. So the largest projected growth in primary energy consumption between 2010 and 2035 will be renewables. The others are pretty flat. They're looking at about 4.8 quadrillion British thermal unit. That is excluding the liquid biofuels. And as far as the liquid biofuels themselves, they're going to use 2.9 quadrillion BTUs. Natural gas, 2.5 quadrillion BTUs. The 2035 shares of other energy sources, including nuclear, coal, oil, and other liquids, are either declining or remaining flat relative to the 2010 levels. This is trying to contrast the historic usage of energy with the projected usage of energy, let's say from 2020 to 2050. You can see the blue line representing the total energy consumption, and the brown line representing the per capita energy consumption. You can see that the per capita energy consumption historically has been higher, on the higher side, and it's going down. You can see that the brown line is going down in the projected per capita energy consumption, whereas the actual total energy consumption is going up in the projected relative to the historic. If you look at the very faint white, light blue line at the very bottom of the screen, it's almost non-existent relative to the total amounts. So that's the renewable energy consumption component of it. You can see that it's going in a very shy way from a very low historic numbers to a higher but still very low projected numbers. This slide shows the US primary energy consumption broken down by the source. Here, petroleum, the pie chart on the left showing the petroleum sitting at 37%, natural gas 29%, coal 14%, nuclear 9%, and the renewable is the green part, very small, at 11%. And then if you take the renewable and break it down into its components, geothermal, solar, wind, biomass, biofuels, wood, and hydroelectric, all of those are
under the category of renewable. And you can see that they are predominantly, and to the perhaps surprise of many people, in the hydroelectric, 25%, wood, which is 19%, and biofuels, 21%, and wind is 21%. Solar is very small, still 6%. Geothermal is 2%, and biomass waste is 4%. This is another way of looking at the energy consumption picture, and that's a snapshot in time in 2017. You can see again the interaction between the primary energy source on the left column and the application areas on the right column. You can see the transportation sector consuming 29%, the industrial sector about 22%, the residential and the commercial sector is about 11%, and the electric power is sitting at about 37%. And you can see that the different lines going from the left column to the right column showing which source is used in which application. This is another picture showing the primary energy production. This is now talking about the production as far as the source of energy. Again, going from natural gas on the very left, the highest 27%, all the way to hydro on the very right at 2%. Again, you can't even see solar there. It's hiding under other 3%. Now, the U.S. energy use picture is predominantly going into 40% of the primary energy is in buildings, and 70% of that energy goes into electricity. The commercial buildings primary energy consumption grew by about 70% from 1980 to 2010, and the Energy Information Administration projects 22% growth between 2010 and 2035. For the residential section, the homes that are built between 2000 and 2005, they use 14% less energy than the homes that were built in the 1980s. And they used 40% less than those homes built before the 1950s. This is showing the areas of the building energy usage on the commercial side. And here you see the space heating and the water heating are the lion's share of the consumption. Space heating 45% and water heating 18%. And then you see all these other little things from lighting to cooking, electronics, refrigeration, computers, etc. They form a smaller percentage. Now you see an asterisk which is adjusted to what they call SEDs. Now this SEDs is really the Energy Information Administration's methodology to make an adjustment to reconcile what they call the supply side state energy data system, or what SEDs is for, and the end user, which is principally the residential energy consumption survey estimates in energy usage. So there is an adjustment that is to be made. If you look at the regulated component, which is lighting and space cooling and space heating and ventilation, water heating and refrigeration versus the the unregulated components, which are cooking, computers, electronics. You can see that the different percentages listed there. For residential section, the same slide, but for residential, you can see space heating again, and of course, lighting is not an insignificant player, 14%. Again, you get the picture of what things look like on the residential side. Now, here are some what they call non-governmental organizations that have been working behind the scenes to reduce the building energy usage. And many of those organizations have actually made a significant dent into improving the energy consumption picture. ASHRAE, for example, they have their building codes, especially 90.1 is a very famous code. The latest revision for that code have been released in 2019. Then they have the International Green Construction Code, or what they call IGCC. There is a 2018 version of it that has also made a contribution. And the International Energy Conservation Code, IECC, that was introduced first in 1998. The latest edition of that is the one that has been approved in December 2019, and they call that the 2021 International Energy Conservation Code. And then, of course, the Environmental Protection Agency have the well-known Energy Star program, and that would identify and promote energy-efficient products and buildings in order to reduce energy consumption and reduce pollution. And of course, the LEED program, which is the Leadership in Energy and Environmental Design, that program promotes a certification system to identify high efficient performance buildings. This is by the Green Building Council. And it provides training as well to people and towards achieving the certification and towards building certification itself. This is what a graphics showing what the non-governmental organizations' efforts has been able to do from going back from the 1975 range, when the first energy crisis happened in 1973, and then in 1979 is the second energy crisis. And then you can see that the introduction of the 90.1 standard saved 14% between the 1980s and the very early and the late 1980s, the mid and the late 1980s. And then further refinements to the standard 90.1 made another 4% savings and another 12% savings. And here we are now talking about, by the time you add all of that, you're almost talking about a 50% reduction due to non-governmental organization effort. The Department of Energy in the United States has set goals. They want to, by 2025, to achieve 75% energy reduction using energy efficiency technologies, and they are making good effort in that. I'm going to show you some examples of things that they have been doing. They also want to create, by 2025, they want to create the technology and the knowledge base for a cost-effective zero energy commercial building concept, what we call ZEBs, zero energy buildings, so that becomes the model for the future. The National Renewable Energy Laboratory has been busy, and they have been working in the area of zero energy buildings. They published, first of all, a definition. There's a book you see on the left side of the screen. That's a common definition for zero energy buildings, which is it's a building that produces enough renewable energy to meet its own annual energy consumption requirements, therefore being able to reduce the use of non-renewable energy in the building section. So this definition applies to also campuses and portfolios and communities, not just buildings. They published a guide for cost control strategies for zero energy buildings. And basically what they did was they assembled recommendations for being able to replicate specific successes of early adopters who have met their energy goals while controlling the while being able to control their costs. They also published a guide for what they call communities of the future. And this is basically a way to accelerate the move towards zero energy. So they call this Accelerating Zero Energy District Master Planning. And this is a guide that provides a user-friendly roadmap for achieving a zero energy in the so-called K through 12 school buildings, the kindergarten through 12th grade. It includes a set of energy performance targets for all climate zones. And you will see that in the United States, there are 8 climate zones. I will show you in a minute. The strategies on how to achieve these energy targets are also provided throughout that guide. You can actually download these from the NREL website. If you Google these names, you should be able to get the link, and you can download these reports for free. Also, the so-called New Buildings Institute, or NBI, this institute has been busy since 2012, when they published a report, a status report, what they call Towards Zero Energy. In 2012, they published a report, and then in 2014, they published another report. It's getting to zero, the 2014 status. And they kept publishing these reports. In 2018, there is, I believe, the latest one they have, and there will be another one coming out in 2020. The 2018 status report, Getting to Zero, I'll talk to you a little bit about what that report contains in just a minute. This is the 2014, from the 2014 report. There was 126 buildings in the United States that were categorized as zero energy buildings, and here they are distributed over the 8 climatic zones in the United States. Now you see on the pie chart, you only see 7, but there are actually 8, and you can see them on the right side of the slide. The zone number 8 is subarctic, and it's only available in Alaska, so it's not in the mainstream, so to speak. And then you have the very cold region, which is region number 7, and the cold region, which is zone number 5 and zone number 6. And then you have mixed humid and mixed dry, and hot humid and hot dry, and then you have the so-called marine zone. Now, the New Buildings Institute and the 2018 report, they published this slide showing the buildings list that includes nearly 500 projects. And you can see that it's on a very steep curve upward, having increased over 700% since that very first report was published in 2012. Now here they have verified buildings, which is in the light green, and then the dark blue is what they call the emerging buildings. They have not been verified, but they are emerging and potentially getting where they could be verified. This is another slide from that 2018 report showing that there are actually 67 zero energy verified buildings and 415 zero energy emerging projects documented by the New Buildings Institute. You can see how the numbers have grown from 2012 to 2014 to 2016 to 2018. If you look at the status report, across the continental United States, and of course Alaska and Hawaii. You see Hawaii is in the very bottom here. Of course, that's not the actual geographical location of it, but they have sort of carved it and put it in there, as well as Alaska. And you can see the number in the different locations in the map. These are projects, zero energy projects by region and by state and by province. In fact, in Canada, there are four provinces. The province of Quebec, the province of Ontario, and the province of British Columbia, and the province of Alberta. All of those are showing non-zero numbers. You got 2 in Quebec, you got 5 in Ontario, you got 1 in you got 7 in British Columbia, and you got 1 in Alberta. And of course, in the United States, you see California on the south, on the west side of the United States, showing 214. Oregon comes next as a strong second at 24. So the California is by far the largest, the state that has the largest number of zero energy projects. And then the second largest would be Oregon, but there's a big difference between the two, 214 versus 24. Now in California, there has been 131% growth in the number of projects. And in the rest of the United States, they divided them into northeast, southeast, southwest, northwest, and midwest, and south central. And then in Canada, they have a category by themselves. They went from they went up by about 50%. This is the picture, or shall I say, was the picture in 2014 compared to the picture in 2018. This is where the number of projects, you can see that in California there was only 10. We went to 214 in 2018. So there's a huge increase there, 131% increase. And you can see that in Florida there was only 3. Oregon, there was only 2. The New Buildings Institute 2018 report also shows the zero energy buildings that are in every climatic zone across the United States. And you can see that the different color codes are showing the different climatic regions. This is the southeast part, which is the very dark red. And then you've got the west, you've got the southwest, you've got the midwest. The different climatic zones being the 8 zones that we're talking about. And these are the categories, zone 1 or 2 or 3 or 7. And they have the A and B because they have different variations, as we indicated that 3 slides ago. These are the verified versus emerging in terms of the square footage, where the dark red is very small, like under 5,000 square foot, and then the dark blue and the purple color is over 100,000 square foot. So you can see that the growth is 88% of the growth has been in buildings over 50,000 square foot, which is where you could make a big dent with these big buildings. This is a slide showing the zero energy buildings based on the building type, breakdown in terms of education buildings versus office buildings, multifamily houses, public assembly, mercantile, public order and safety, warehouse and storage. And in the education, you can divide them into higher education and general education and the K through 12 education. And this is showing the same thing based on building ownership, the distribution versus private for-profit versus private multifamily, private nonprofit, public county, public city, public state, and public federal. And you can look at the numbers, you can read it for yourself. This is also from the same report showing the growth by building sector, public sector versus private sector. You can see the private sector has picked up a pretty good amount in the past 6 to 8 years or so. The public sector continues to have the lion's share, though, 54% versus 46%. This is showing the growth by building ownership, the same information but in a graphical form. And the vertical axis is showing the building count. And then this is a 2017 snapshot of the so-called ZEPI score. Is a jurisdictional score which ranks the states based on their adoption of energy policy, their adopted energy policy. If it's favorable towards net zero or less favorable towards net zero, they give you a score. So happens is the score, and I'll talk about the score in a minute, perhaps in the next slide. Okay, let's go back to this slide. So this is showing the score. The best score is zero score. If you want to have a zero score, you're absolutely zero energy. So, for example, a score of 75 relative to a building that has a score of the state that has a score of 75 versus one that has a score of 100, it uses 30% less energy if you have a score of 70, or 25% less energy if you have a score of 75. The New Buildings Institute also published a report in 2019, May 6, 2019, on net zero energy. And in that report, they give you, they have a database now. It's an NBI database for zero buildings. And you can actually go online and you can actually work with that database to interact. It's an interactive database. You can select what you want and it will give you the answers that you need. The Florida Solar Energy Center, Energy Research Center at the University of Central Florida, it's known as FSEC. This has been in existence now for a good since the 1970s, and under the Carter administration, I believe in 1979, during the second energy crisis, and there was a big move towards solar energy. And in fact, the White House had solar panels on top of the White House at that time during the Carter administration. They developed a home energy rating system that would rate the buildings in the same way that it rates the state. So here, a building that has a score of 70 is projected to use 30% less energy than one that has a score of 100. And a score of 0, of course, is the ideal one. They also published a report by two famous researchers there at the FSAC, Danny Parker and Delia Agostino, back in 2016, and they talked about the comprehensive modeling of optimal paths to reach nearly zero energy buildings for new constructions, and they focused on Europe. In the report, they described results that they obtained from modeling net zero energy buildings for new construction in Europe using the energy performance software Energy Plus. The model actually is able to perform hourly sequential simulations showing how to best achieve nearly zero energy home design at the lowest possible cost in about 36 representative locations across Europe. One of the findings that they came up with was that energy reductions by 80% are possible and can be done in an economical way for new construction. And the way they do that, they use a mix of selected measures from varying strongly with climate. These results show that a broad approach mixing renewables and energy efficiency measures can be used in a feasible way to achieve the 80% reduction. Now I would like to shift to the California experience. And California has several federal labs. One of them is the so-called Lawrence Livermore National Lab. They have another one called the Lawrence Berkeley National Labs. And those two are leading research institutions in energy. But the Lawrence Berkeley National Lab focuses on buildings. The report that you're looking at here is a report that outlines ways where California could reach the goal of becoming carbon neutral by 2045. And this is a picture showing Governor Jerry Brown, who is the former governor of California. He is the one on the right side of the person holding the scissors. Jerry Brown was the governor of California for 2 consecutive terms in the 1970s, and then became a governor of California again most recently, before Governor Newsom was the governor of the current governor of California. And they were very aggressive. California has been extremely aggressive to achieve net zero buildings. They have, California has close to 40 million people living in the state, and they boast the 6th largest economy. They have an economy that's larger than most countries in the globe. So they're considered to be the trendsetter as far as the United States. If it happens in California, then most likely it will happen in the rest of the United States at some point in the future. So they have been by far the front runner as far as zero energy research and activities, and Oregon is number 2, as I mentioned earlier. They set a bold course to achieve statewide zero net energy in the next 2 decades, and all the new residential construction now will be zero net energy by 2020 in California, and the new commercial construction will be net zero by 2030, and then 50% of existing commercial buildings in California will be retrofitted to be net zero by 2030. This is going back to the climate type and building type and the building energy use area. You can see the 8 climatic regions in the United States. Don't forget to count Alaska, because it has a climate zone by itself. And then it also shows you the different applications where the energy goes, depending on the pie chart at the bottom there. Okay, so you can see that go back to here. You can see that there is a mixed humid region in the so-called heartland of the United States here, where you've got Missouri, you've got Kansas, you've got Arkansas, you've got Alabama, Oklahoma, Tennessee, Georgia. All of those are in the mixed humid. And then you've got the hot and humid, which is in the southeast, and that's in Georgia, that's in southern Georgia, and in all of Florida, in the Panhandle, in Louisiana, and in Texas. And then you've got the hot dry, or the so-called mixed dry, sometimes hot dry / mixed dry, and that includes New Mexico, and it includes a portion of Texas, the northwest part of Texas where Lubbock is, and it includes a good amount of California in the Mojave Desert and in regions that were away from the coastline, excluding Los Angeles and San Diego and San Francisco. All of the coastal cities in California are outside that zone. It's more of a Mediterranean climate there. And of course, you've got the Pacific Northwest. It has a climate of its own in the so-called marine climate, and that includes the one in Los Angeles, San Francisco, and in San Diego. And I call it Mediterranean climate. They call it here marine climate. There have been 10 buildings that are zero energy, pioneering zero energy buildings in the United States. I'm going to show you only one of them in Hawaii, but they were distributed as 3 in California and 2 and 6 as California Zone 3. I was distributed in California, which is Zone 3, Vermont, which is Zone 6, Wisconsin, which is Zone 6 as well, Ohio, Zone 5, and Hawaii, Zone 1, Minnesota, Zone 6. They cover both climate, the cold climate and the warm climate. There were 2 campus buildings, 1 retail building, and 1 single-family building. And none of those 10 buildings are more than 14,000 square foot. The average is about 5,500. If you look at the Kupuni Village in Hawaii, which is Zone 1, this is the building actually that we're looking at. You can see that zero energy buildings right there, and that's one of the 10 pioneering buildings in the United States. There was also the so-called solar decathlon, which students compete to build houses powered exclusively by the sun, and you can see that this is a snapshot of one of those days where they gathered to showcase their buildings. Now, for the remaining few minutes, I would like to talk to you about some examples of recent energy efficiency projects in different areas, and I'm going to take a couple of them to talk about. But let me first give you a quick rundown of what we have in the HVAC area, the heating, ventilating, and air conditioning area. They have what they call an air source integrated heat pump project. All of those were funded by the Department of Energy at some point. A cold climate heat pump. Now, you know that heat pumps are not very effective in cold climates, because what you're basically doing is you're converting the condenser, which normally would reject heat to the outside in the summertime. That condenser operates like an evaporator, and it basically absorbs heat from the outside and dumps it into the building, and therefore it becomes a heat pump. It takes the heat from a low temperature source at the outside and dumps it into the inside, which is a higher temperature sink. It doesn't work very well in the cold climate because of the fact that the outdoor temperature is very low. And as you may or may not know, for the coefficient of performance, when the lower temperature becomes lower, the coefficient of performance also becomes lower. So you wanna create a heat pump that can operate in a lower temperature environment. That would be would be a big achievement in and of itself. They also have what they call a next generation rooftop unit that would sort of be have a quantum jump in efficiency relative to what the existing rooftop units now are. Residential absorption heat pumps. Absorption heat pumps they use lithium bromide or ammonia water for the working fluid, and you know that the coefficient of performance for those absorption systems is much smaller than the vapor compression counterparts. They also work on commercial integrated heat pump with thermal storage. That's a big deal, where you would have a heat pump along with a thermal storage capability attached to it. And they also have a project on separate, sensible, and latent cooling, and another project on a membrane-based air conditioning system. In fact, we have a professor the University of Florida, who has been working on these technologies for a good while now, and he's been funded very well by the ARPA-E, which is an agency of the Department of Energy, the Advanced Research Project Agency, Energy, ARPA-E, which is modeled along the lines of ARPA, which are the Advanced Research Project Agency, and the DARPA, which is the Defense Advanced Project Agency that have been serving the Defense Department for a long while. They also have a novel solar absorption cooling system to reduce peak loads. And in the area of water heating, they have this absorption heat pump water heater concept, and a commercial absorption heat pump water heater project, and a carbon dioxide heat pump water heater project. And they also have a residential absorption heat pump water heater project, and a combined water heater, dehumidifier, and evaporative cooling device that also is being developed, and a commercial carbon dioxide heat pump water heater and maximum technical efficiency electric heat pump water heater with a low global warming potential halogenated refrigerant project. So you can see that there's a lot of good causes that are being sought out by combining all of these good technologies into one. Other examples of projects that are being worked on include a miniaturized air to refrigerant heat transfer device by the University of Maryland. I'm going to talk to you about that in just a minute, and tell you where the technology is in that field. There's a gas heat pump for building space heating. This is a company called Stone Mountain Technologies that have been very well funded by the U.S. Department of Energy for the past many years, and they are working very hard on this gas heat pump for building space heating. And then the Lawrence Berkeley National Lab is working on a highly insulating windows using smart automated shading. I will talk to you more about that in just a minute, show you how that works. And a dynamic window program at the National Renewable Energy Laboratory, and a dynamically responsive infrared windows coating at the Pacific Northwest National Lab in Washington State, and what they call a next generation building envelope materials at Oak Ridge National Lab, and building integrated heat and moisture exchangers, which I believe that there is a professor at the University of Saskatchewan is working on what they call integrated heat and moisture heat exchangers, or sometimes we call them enthalpy heat exchangers. This is the snapshot of a picture showing this concept behind the miniaturized air to refrigerant heat exchanger at the University of Maryland. Professor Radermacher at the University of Maryland is actually the one working on this project, and the idea here is to develop next generation heat exchangers for heat pumps and air conditioners with a performance target of 20% less volume, 20% less material, 20% more performance than the existing designs. And the market target is to be in production within 5 years. Actually, there are some that are in production now. And they have partnered with Oak Ridge National Lab, and Lovata International Copper Association, Wieland, and Heat Transfer Technologies among their partners. This is where the slide that they showed in one of their presentations, where you see the compactness on the vertical axis versus the so-called port hydraulic diameter on the horizontal axis. The port hydraulic diameter is a number that indicates or shows how big the heat exchanger is. So the smaller the port hydraulic diameter, the smaller it is. And of course, we're talking mini heat exchangers here, miniaturized. These are very small. We're talking in millimeter size. The compactness, on the other hand, is how much surface area can you have for a given volume. So it's measured in terms of centimeters squared per centimeter cube. So the smaller the worse. The smaller the worse. In other words, you want to have a big surface area for a given volume. So you want to be at the top. You want to be at the very top left corner if you want to have a high compactness. But if you want to have a small hydraulic diameter, then you want to be at the bottom left. So if you combine that with if you combine the two objectives, then you definitely want to be at the top left, which has a small hydraulic diameter port and a high compactness. So that's why you see only one data point at the very top between 100 and 120 on the top left corner of that diagram. You see a lot of things at the bottom left, and you definitely see a lot of things along the whole gamut of port hydraulic diameters, but unfortunately it was a small compactness. So all of those are small compactness, but high and large hydraulic diameter. This is another picture showing the different types of heat exchangers that you can use to achieve that. This is showing the heat exchanger volume, and it shows you the pressure drop associated with each technology here. Remember, in heat exchanger technology, your objective is not just to maximize heat transfer, but to also minimize the pressure drop. The problem is maximizing heat transfer with minimal pressure drop and therefore minimal power consumption. This is the project pertaining to the Lawrence Berkeley National Lab, and I will be finishing here shortly. This is a smart shading system. They have shading that works. They have an algorithm whereby the shades will open and close based on whether you want heating or cooling, and it would adjust it exactly in a way that would based on the external temperature and the internal temperature. So here you decide if the indoor temperature is between the heating limit and the cooling limit, then you go through this algorithm. If it's greater than the cooling, then you go through this algorithm, and if it's less than the heating set point, then you go through this algorithm. So this is an algorithm that Lawrence Berkeley National Lab has developed, and the shade will actually adjust its position accordingly. So in conclusions, there is an effort going underway at finding a solution to the energy problem, global energy problem. Part of the effort is directed at establishing a permanent energy system by investigating renewables, but the other part is directed at finding better and more efficient ways of conserving the existing energy sources that we have. And examples in both of these have been sort of given. I haven't really gone too deep into the renewables, but for lack of time. The U.S. is making steady but measured steps towards net zero. Significant progress has been made under the Obama administration in the area of energy efficiency, and it's also in transportation, in the transportation sector, where they raised the so-called CAFE standards for energy efficiency for cars and trucks. The DOE is pursuing an aggressive policy in the area of energy efficiency and energy conservation, as you saw some of the projects I showed you. Significant progress has been also made in the area of environmental protection, to curb the greenhouse gases. I know that the U.S. pulled out of the Paris Climate Agreement, but before that they were part of it, and much more needs to be done. California is always leading by example, and it's possible that there would be policy shifts and setbacks under successive U.S. administration. And that concludes my presentation. Thank you very much.
Dear sir, the session was really informative. Thank you very much. I, Nityananda BS, working as assistant professor in the Department of Mechanical Engineering. So it's a great privilege to propose vote of thanks to all who have helped us in making this international webinar a great success. First of all, I would like to express my sincere thanks to Dr. S A Sherif, Professor, Department of Mechanical and Aerospace Engineering, University of Florida, for making excellent presentation and making this webinar a grand success. Thank you, sir.
Thank you.
I would like to express my sincere thanks to our principal, Dr. B. Sadashivegoda, for helping us in conducting this webinar. Thank you, sir. I would like to express my thanks to our HOD, Dr. G.V. Naveen Prakash, for his moral support and guidance for conducting this webinar. Thank you, sir. I would like to propose vote of thanks to the coordinators of this webinar who have taken utmost care in conducting this webinar and making this webinar a great success. Thank you. I would like to express my sincere thanks to ISRE Mysore chapter for helping out in conducting this webinar. Thank you all. Finally, I would like to express my sincere thanks to staffs of Department of Mechanical Engineering for helping in conducting this webinar, and also to all the wonderful participants who have turned up in large numbers and helped us in making this webinar a resounding success. Once again, I thank you all for your cordial participation and cooperation. Thank you, one and all. So, kind attention participants, with regard to certificate, we're going to soon we are going to share a new link in the comment section. I think already the new feedback link is shared. We just give you a feedback about this webinar, and the certificate will be mailed to your mail ID. Thank you, one and all. Thank you, sir.
Thank you so much.